Hello all, welcome to this video on machine learning. Today I'll be talking about an example of logistic regression, perceptron, naive Bayes, and decision trees. Now let us begin with an example of logistic regression. Let us say we have a model that can predict whether a person is male or female based on their height. Given the height of a person is 150 centimeter, and we have the coefficients given as B0 and B1, which is minus 100 and 0.6 respectively. From this, we can calculate the probability of male given a height of 150 centimeter or more as P of male given height is equal to 150. We will use EXP instead of E in the equation. As we already know, the formula for logistic regression is y is equal to e raised to b0 plus b1x divided by 1 plus e raised to b0 plus b1x. On substituting the values, we will get the answer of y as 0.00454, or the probability of near zero that a person is male. In practice, we can use these probabilities directly. Because this is a classification and we need a correct answer, we can snap the probabilities to a binary class value. For example, 0 if the probability of male is less than 0.5 and 1 if probability of male is greater than or equal to 0.5. Now let us look into perceptron. Now a perceptron works by taking in some numerical inputs along with what is known as weights and bias. It then multiplies these inputs with the respective weights, which we call the weighted sum. These products are then added together along with the bias. The activation function takes the weighted sum and the bias as inputs and returns a final output. Now a perceptron consists of 4 parts: input values, weights and a bias, a weighted sum, and activation function. Now assume that we have a single neuron and 3 inputs x1, x2, x3 multiplied by the weights w1, w2 and w3 respectively as shown in the figure. As we already saw, the idea is simple here. Given the numerical value of the inputs and the weights, there is a function inside the neuron that will produce an output. Now what is this function? So one function may look like y is equal to x1 w1 plus x2 w2 plus x3 w3. This function is called the weighted sum because it is the sum of weights and inputs. It looks like a good function, but what if we wanted the outputs to fall into a certain range like 0 to 1? Now for this, we'll do something known as the activation function. An activation function is a function that converts the given input, which is the weighted sum, into a certain output based on a set of rules. Now there are different kinds of activation functions that exist, like a hyperbolic tangent that is used to output a number from -1 to 1, and logistic function that is used to output a number from 0 to 1. Activation functions also allow for non-linear classification. Now bias is a threshold that the perceptron must reach before the output is produced. So the final neuron equation looks like y is equal to sigma of weight into input plus the bias value, which is represented in the figure. Now, where are perceptrons used? Now they are the building blocks of neural networks. It is typically used for supervised learning of binary classifiers. We'll try to understand this through an example. So let us take a simple perceptron. So in this we have input x and y, which is multiplied by the weights wx and wy respectively. It also contains a bias. Now let us also create a graph with 2 different categories of data, which is represented with blue and red dots as given in the figure. Notice that the x-axis is labeled after input x and y-axis is labeled after input y. Suppose our goal is to separate this data so that there is a distinction between the blue dots and the red dots. Now, how can we use the perceptron to do this? A perceptron can create a decision boundary for a binary classification where a decision boundary is regions of space on a graph that separates different data points. Let us see an example to better understand this, where wx is taken as 0.5, wy as 0.5 and b as 0. Then the function for the perceptron will look like 0.5x plus 0.5y is equal to 0, and the graph will look like as it is shown in the figure. Now let's suppose that the activation function in this case is a simple step function that outputs either 0 or 1. The perceptron function will then label the blue dots as 1 and the red dots as 0. In other words, if 0.5x plus 0.5y is greater than or equal to 0, then it's 1. And if 0.5x plus 0.5y is less than 0, then it is 0. As shown in the figure, this function creates a decision boundary that separates the red and blue points. Now let us look into naive Bayes. Naive Bayes is a probabilistic algorithm that's typically used for classification problems. It is simple, intuitive, and yet performs surprisingly well in many cases. For example, spam filters that is used in email app are built on naive Bayes. Let x is equal to x1, x2, etc. xk represent k features. Y is the label with k possible values, which are classes. Now from a probabilistic perspective, xi element of x and y are random variables. Then the value of xi is x and yi is y. In order to make the classifications, we need to use x to predict y. This can be rewritten in the equation as p of y equal to y given x equal to x1, x2, etc. xk. Find the most likely y, which is prediction, which is equal to argmax function of p of y equal to y given x equal to x1, x2, etc. xk. Now, this is the basic idea of naive Bayes. According to Bayes' theorem, p of y given x is equal to p of x given y into p of y by p of x. We have already seen this in one of the previous videos, which can be also written as posterior is equal to likelihood into prior by evidence. This is a rather simple transformation, but it bridges the gap between what we want to do and what we can do. We can't directly get p of y given x, but we can get p of x given y and p of y from the training data. We will see an example here. The given figure shows the weather data set from the University of Edinburgh. In this case, x is equal to outlook, temperature, humidity and windy, and y is equal to play. Now p of x given y and p of y can be calculated as p of y equal to play, which is given by number of plays by number of play plus number of not play. From the table, we get the values as 9 for the number of plays and 5 for the number of not plays. So the value will be 9 by 14. Now p of x is equal to sunny given y equal to play is written as number of play and sunny by number of play. From the table, we get the values as 2 by 9. Now theoretically, it's not hard to find p of x given y. However, it is much harder in reality as the number of features grow. In the figure, we see that 7 parameters are needed for this 2-feature binary data set. P of x is equal to x1, x2, etc. xk given y equal to y is called a parameter in naive Bayes. So if xj for all j is binary, then we have 2 raised to k plus 1 minus 1 parameters. Having this number of parameters in a model is impractical. To solve this problem, a naive assumption is made. We pretend that all the features are independent. That is, if x1 and x2 are independent, then p of x1 comma x2 given y is equal to p of x1 given y into p of x2 given y. P of y given x will be p of y into product of p of xi given y by p of x, which is the new naive Bayes classifier. So for the table given here, we will see that the naive Bayes will need only fewer parameters, that is 4 in this case. So here for xj for all j when it's binary, we have 2k parameters. Now that's a big deal. We changed the number of parameters from exponential to linear. This means that naive Bayes handle high dimensional data very well. Now we look into categorical and continuous features. For categorical features, the estimation of p of xi given y is easy. P of xi is equal to x given y equal to y is given by number of xi equal to x, y equal to y divided by number of y equal to y, which is the calculation of likelihood of categorical features. However, there is one issue, that is, if some feature values never show, maybe due to lack of data, their likelihood will be 0, which will mean that the whole posterior probability will be 0. Now, one way to fix this problem is by Laplace estimator, that is by adding imaginary samples, usually 1, to each category. So, p of xi equal to x given y equal to y will be number of xi equal to x, y equal to y plus 1 by number of y equal to y plus m. So, here m will be the number of data points such that xi equal to x and y equal to y. Now, for continuous features, there are two choices, discretization and continuous naive Bayes. Discretization works by breaking down the data into categorical values. The simplest discretization is uniform binning, which creates bins with fixed range. There are more complicated ways also to solve this, like recursive minimal entropy partitioning or SOM based partitioning. The table here is discretizing continuous feature for naive Bayes. Now the second option available is to utilize the norm distribution. If the features are continuous, then the naive Bayes algorithm can be written as p of y given x is equal to p of y into product of f of xi given y by f of x. For instance, if we visualize the data and see a bell curve-like distribution, it is fair to make an assumption that the feature is normally distributed. Now the first step here will be to calculate the mean and variance of the feature for a given label y, where S is the data points with y equal to y, which is given by mu dash is equal to sigma s xi by length of s, and sigma dash square given by 1 by m minus 1 sigma s xi by minus mu dash the whole square. Next, we'll calculate the probability density function, which is given by f of xi equal to x given y equal to y, which is equal to 1 by root of 2 pi sigma dash square into e raised to x minus mu dash the whole square by 2 sigma dash square. There are also other distributions like Gaussian naive Bayes, multinomial naive Bayes, complement naive Bayes, and Bernoulli naive Bayes. Although these methods vary in their form, the core idea behind is the same. Assuming the feature satisfies a certain distribution, estimating the parameters of the distribution, and then get the probability density function. Even though the naive assumption is rarely true, the algorithm performs surprisingly good in many cases. It can also handle high dimensional data well, and it is easy to parallelize and handle big data also. It performs better than more complicated models when the data set is small. However, the estimated probability is often inaccurate because of the naive assumption. So it is not ideal for regression use or probability estimation. Now, when the data is abundant, other more complicated models tend to outperform naive Bayes. Now we look into decision trees. In simple words, a decision tree is a structure that contains nodes, which are rectangular boxes, and edges, which are arrows, and is built from a data set, that is a table of columns representing features or attributes and rows corresponding to records. Each node is either used to make a decision, which is known as decision node, or to represent an outcome, which is known as the leaf node. Now given here is a decision tree example. It shows a decision tree that is used to classify whether a person is fit or unfit. Now the decision nodes here have questions like, is the person less than 30 years of age? Does the person eat junk, etc.? and leaves are one of the two possible outcomes, which is fit and unfit. Now, looking at the decision tree, we can make the following decisions. If a person is less than 30 years of age and does not eat junk food, then he is fit. If a person is less than 30 years of age and eats junk food, then he is unfit, and so on. The initial node here is called the root node, which is colored in blue. The final nodes are called leaf nodes, which are colored in green, and the rest of the nodes are called intermediate or internal nodes, which are colored in yellow. The root and intermediate nodes represent the decisions, while the leaf nodes represent the outcomes. Now let us look into ID3 algorithm. ID3 stands for iterative dichotomizer 3 and is named such because the algorithm iteratively or repeatedly dichotomizes or divides the features into two or more groups at each step. It uses a top-down greedy approach to build a decision tree. In simple words, the top-down approach means that we start building the tree from the top, and greedy approach means that at each iteration, we select the best feature at the present moment to create a node. Most generally, it is used for classification problems with nominal features only. Now we'll see an example for the same. For this, we are taking the sample data set of COVID-19 infection. On examining, we see that the columns that is used to make decision nodes, that is the breathing issues, cough and fever, are called the feature columns or just features, and the column used for leaf nodes, for example, here it is infected, is called the target column. Now ID3 algorithm selects the best feature at each step while building the decision tree. Now, how is it done? It is done using calculation of information gain. Now, information gain calculates the reduction in the entropy and measures how well a given feature separates or classifies the target classes. The feature with the highest information gain is selected as the best one. Entropy is the measure of disorder, and entropy of a dataset is the measure of disorder in the target feature of the dataset. In case of binary classification, where the target column has only two types of classes, entropy is 0 if all the values in the target column are homogeneous or similar, and will be 1 if the target column has equal number of values for both the classes. We denote the data set as S. So for here, the entropy will be calculated as minus sigma pi into log of pi to the base 2, where I varies from 1 to n, where n is the total number of classes in the target column. In this case, n is 2, where it is yes or no, and pi is the probability of class I, or the ratio of number of rows with class I in the target column to the total number of rows in the dataset. Information gain for a feature column A is calculated as entropy of S minus sigma mode of SV divided by mode of S into entropy of SV. Here SV is the set of rows in S for which the feature column A has a value V. Mode of SV is the number of rows in SV, and mode of S is the number of rows in S. Now we'll look into the steps involved in the ID3 algorithm. We'll calculate the information gain for each feature first. Considering that all rows do not belong to the same class, we'll split the data set S into subsets using the feature for which the information gain is maximum. Then we make a decision tree node using the feature with the maximum information gain. Now if all the rows belong to the same class, then we make the current node as a leaf node with the class as its label. And we repeat this for the remaining features until we run out of features or the decision tree has all the leaf nodes. We'll apply this technique on the example we saw before. From the total of 14 columns in our dataset, there are 8 rows with the target value yes and 6 rows with the target value no. So the entropy S will be calculated by substituting these values into the equation, and we'll get the value as 0.99. Now we need to calculate the information gain for each feature. For the fever feature, there are 8 rows having the value yes and 6 rows having the value no. This is shown in the table given here. Also, in the 8 rows with yes for fever, there are 6 rows having target value yes and 2 rows having target value no. And in the 6 rows with no, there are 2 rows having target value yes and 4 rows having target value no. And the image at the bottom shows the calculation of information gain for fever. And the final answer we get is 0.13. Next, we need to calculate information gain for the features, cough and breathing issues. We do it in the similar way and the answers will be 0.04 for cough and 0.4 for breathing issues. Since the feature breathing issues have the highest information gain, it is used to create the root node, and after the initial step, the tree will look as shown in the figure. Next, from the remaining 2 unused features, namely the fever and cough, we decide which one is the best for the left branch of breathing issues. Now, since the left branch of breathing issues denotes yes, we'll work with the subset of the original data, that is, the set of rows having yes as the value in the breathing issues column. So there are 8 such rows as shown in the figure. Now we'll calculate the information gain for the features fever and cough using a subset which we call as set breathing issues yes, which is given by SBY. And then we'll see the values as 0.2 for fever and 0.09 for cough. Now the information gain for fever is greater than that of cough, so we select fever as the left branch of breathing issues. Now the tree will look like as it is shown in the top figure. Next, we need to find the feature with maximum information gain for the right branch of breathing issues. Since there is only one unused feature left, we have no other choice but to make it the right branch of the root node. And the new tree will look like it is shown in the figure, which is at the bottom. Now there are no more unused features, so we stop here and jump to the final step of creating the leaf nodes. For the left node of fever, we see that the subset of rows from the original data set that has breathing issues and fever both values to yes, which is shown in the figure. Now since all the values in the target column are yes, we label the left leaf node as yes, but to make it more logical, we will label it as infected. Similarly, for the right node of fever, we see the subset of rows from the original data set that is having breathing issues value as yes and fever as no, which is shown in the figure. Here not all but most of the values are no, hence no or not infected becomes our right leaf node. And now the tree will look as it is shown in the figure. We'll repeat the same process for the node cough. However, here both the left and right leaves turn out to be the same, which is no or not infected. Now this is one of the drawbacks of ID3, which is that it doesn't do something called as pruning. Now pruning is a mechanism that reduces the size and complexity of a decision tree by removing unnecessary nodes. Another drawback of ID3 is overfitting or high variance, that is, it learns the data set it used so well that it fails to generalize on new data. That's all for now. Thank you for watching.